Now let's break down the solution for you here. So we're given 1 joule of energy and 1/millionth of a coulomb, 1 microcoulomb. So to find voltage, we just take the energy divided by the charge. So in this case, we have 1 joule divided by 1 times 10 to the negative 6, or 1/millionth of a coulomb, a microcoulomb, and that'll just simply give us 1,000,000 volts. So what's crazy is Van de Graaff generator can have super high voltages, anywhere from 200,000 to 500,000 to 1,000,000 volts, but not necessarily dangerous because it's a little bit of energy and a little bit of charge. So again, it could be like a squirt gun, a lot of pressure, but you're not going to drown, getting shot by a squirt gun. But a fire hose you'd have to worry about there. Finally, we have one last slide, derive 2 equations for finding the potential difference in a uniform field versus a point charge. In other words, how do you find the voltage for a uniform field, which would be like a battery? So batteries usually just have 2 metal plates that are dissimilar, and usually a weak acid called electrolyte. And one has higher electronegativity than another, and so we set up an electric potential. Potential energy for electricity is QED, where Q is charge, E is the strength of the electric field, and D is the distance between the plates. This looks like gravitational potential energy, which would be MGH, but in electrical potential energy, it's QED. And then voltage is potential energy per charge. So if we substitute in QED for PE, we get QED over Q, and what's nice is the charge actually cancels out. So in other words, we can find the voltage for a uniform field, like a pair of parallel plates inside a battery, by just simply taking the strength of the electric field multiplied by the distance. Next, if we have a point charge where the field is not uniform, substituting in for the electric field equation, the electric field about a point charge, which is KQ over D squared. So when we do that, we substitute in here. We substitute in the E into the V equals ED equation. Then we have KQ over D squared, but there's a D on top, so one of the D's drop out. So in other words, the voltage around a source of charge, we just take the Coulomb's constant K, and then we multiply it by Q, the strength of the source of charge, and then we divide it by the distance. So in other words, it's kind of common sense. If you have a bigger charge, if we charge up a Van de Graaff generator more, it's going to have more voltage, and then it's inversely proportional to the distance as we get closer. So the only thing that's tricky is it's not distance squared when it comes to electric potential. But when it comes to force, that follows Coulomb's law, and that obeys the inverse square law. So finally, we're going to wrap up with 2 last concept check questions here. So first one is true or false? An object with twice the electric potential as another has twice the electric potential energy. And defend your answer. Let's give you a minute, see if you figure this out here.